Good morning, everybody. Welcome to Data Plus AI Summit. My name is Stephen Yu. Um, so before COVID, I used to do this thing where I'd have you kind of get up and high five the person next to you just to make things not awkward for the next 40 minutes. So if you need to do that, you can. But if not, you can just kind of listen to me kind of ramble on for the next 40 minutes. So who am I? Who is this person standing in front of you talking about performance? Well, I'm an SA here at Databricks. I've been with the company now for just under 8 years. And throughout that time, I've seen and worked on a lot of really interesting performance problems and a lot of interesting screening use cases. So I've tried my best to kind of distill those things, those lessons down into some generalizations that I'm going to share with you today. Cool. So before we begin, you will probably see this slide in every, there's live dictation, that's cool. You're probably going to see this slide in every presentation that you're here, that you visit at Summit. And it basically says that I can't make any promises. Everything in the presentation is informational only and subject to change, namely the product name during Thursday morning's keynote. So definitely attend that. Okay, so I like to start my presentations with a quote. This one is by a fictional character in a 2006 comedy about a race car driver named Ricky Bobby, portrayed by the legendary Will Ferrell. I want to go fast. That's what we're going to talk about here today. So, agenda is very simple. We're going to talk about some key factors that affect performance. We're definitely going to touch on cost optimization, talk about some of the knobs that you have, some of the controls that you have there. And then finally, what we've built into Lakeflow DLT to kind of make all of this easier for you. Now's your chance to escape. Just kidding, you can leave whenever you want. All right, so let's get started. Key factors that affect performance. Now, years ago, I bought an Apple Pencil to, make these illustrations and drawings for presentations. And I finally got around to actually using it. So the illustrations are going to kind of suck. Apologies. Did you know that Apple Pencils die if you don't keep them charged? All right, so we're talking about DLT. We're probably talking about ETL workloads. So you can oversimplify and kind of break down an ETL workload into 3 core components. All right, there's a read component. There is a do something interesting after I've read my data component. Then there's a persist this data somewhere. All that hard work. And for those of you that are familiar with how Spark works, it's really, really good at processing lots of data because it's able to take a big problem and break it down into a bunch of smaller problems. And for the Spark experts that are in the room, you might recognize that there's a Spark configuration that kind of controls how Spark parallelizes things. It's called max partition bytes. I think it's 128 megabytes is the default size. Has its roots from the Hadoop era, for those of you who remember. That was the HDFS block size for most commercial Hadoop distributions, 64 megabytes for open source. Anyway, we're able to take big block of data, break it up into units of work that we call Spark partitions. Okay, and then we go and assign a CPU to go and do some work with that partition of data. All right, and then do some interesting things. I don't consider decompression an interesting thing, but it's often a very necessary thing. You're probably shuffling some data. You're probably doing some joins. You're probably doing some math. Probably doing some kind of aggregation. And then you take all of this stuff and you write it back out to cloud storage or to disk somewhere. Okay, and you're probably coalescing that while you're doing so. So what are all the things that can possibly go wrong in this process? No, I did not draw that picture with my Apple Pencil. I wish. That is a AI prompt generated image. Apparently, when you ask it to draw you a picture of a computer bottleneck, you get 4 very sad components staring at an empty wine bottle. Maybe that's why they're sad. Things that can go wrong. Well, compression and decompression are CPU-heavy activities. You might be working with deeply nested complex data types, oddly specific, which in turn causes things like disk spill. You might be running into network latency issues. Maybe you picked an instance type that was kind of small, didn't quite have the same amount of network bandwidth, or maybe you just didn't have enough parallelism. Maybe you're working with smaller amounts of data and that 128 megabyte default max partition bytes is too big. So, I mean, you can basically classify all of these things as resource-based issues. So to start with the first one, we have the concept of a CPU-bound workload. Can anyone take a guess what that means? Nobody knows? I'm just kidding. So this is obviously where your CPU is your bottleneck. Where you're doing lots and lots of work on the CPU. You're doing lots of math, basically. And that is a terrible illustration of a CPU-bound graph. Just pretend the CPU is pegged at 100%. The next type is the memory-bound workload, where, surprise, surprise, this is where you don't have enough memory and you're spilling the disk or you're hitting out-of-memory issues. Typically happens when you're working with data types that compress really well on disk, but as soon as you read it, it kind of blows up like 10x in memory. And then finally, the third type would be an IO-bound workload. Not surprisingly, limited by input-output operations. So reading data from cloud storage, reading data from disk, spilling data to disk. How do we classically address these sorts of problems? Well, the easiest thing that you can do is change the instance type, right? That's the lowest, easiest hanging fruit. And in every major cloud provider, you have these different classes of VMs, okay? I want to mention something about the compute optimized one. So we tend to forget that, since you're just staring at a list of options that says this machine type has 4 cores or 8 cores or 16 cores, we have this tendency to forget that not all cores are created equal. So who remembers the CPU clock cycle or clock speed wars of like the 90s and the 2000s? Yeah. My first computer was I think a 486 SX2 66 megahertz processor with 2 megabytes of RAM. And then in middle school, my family upgraded to a Pentium, MMX technology. That was awesome, 166 megahertz. And the performance was amazing. It screamed. But the point is, not all CPU cores are created equal. If you're dealing with a aggregation-heavy CPU-bound workload, it might behoove you to use better CPUs. There's also general purpose. That's a really good starting point. These ratios, it basically means for every 1 CPU core, you have 2 gigs of RAM or 4 gigs of RAM. In a memory-optimized instance type, you have 8 gigs of RAM. And in an IO-optimized instance type, you have basically your memory-optimized instance with SSDs. So let's talk about improving memory performance. I mentioned disk spill several times, and as an SA here, over the last 8 years, I've seen, this is probably like the #2 most common problem that I see that customers have to deal with. Now, you can historically deal with disk spill a few ways. Obviously, the easiest one is increase the amount of core memory that you have on your machine. But you're like, well, I've already done that. I'm already using a memory optimized instance type. I'm still running out of memory. What do? I'm still spilling the disk. Well, what else? The other thing that you can do is basically, again, think back to how what we were talking about, how Spark does work. It breaks things up into units of work. So I'll give you an example. Let's say you're reading a 1 gigabyte file, okay? And it's compressed really, really well. That 1 gigabyte file, when decompressed, blows up 10x. But you're working with a node that has, let's say, 8 gigs of RAM. So if you were to go and have Spark read that 1 gigabyte file, it's going to go and break it up into 8 partitions. okay? 128 megabyte partitions into 1 gig. And then it's going to go, and let's say you're running this on a VM with 8 cores for the sake of example. It's going to go and blow up this 1 gigabyte file. It's going to become 10 in memory. It's going to spill the disk. And then you're going to be sad, just like this clip art. So what can we do? Well, max partition bytes is configurable. We can reduce the amount of work that you're doing at any given time. So if you say change max partition bytes 128 down to 64, then instead of 8 units of work, you've created 16 units of work, 16 partitions. But you have a fixed number of CPU cores, right? Fixed number of task slots. So at any given time, you're now processing half the amount of data. That's one way you can address it. Now, the number one problem that I see when dealing with performance problems, I/O performance, and it kind of pretty much just boils down to how do we minimize the amount of work that we're having to do? And I have this conversation often. If you want if big data performance is all about, like, how can I reduce the amount of work I need to do and still get the correct answer? So classically, we would solve this using strategies like partitioning or clustering using Hilbert curves and KD trees, or some kind of a indexing strategy like Bloom filters. We'll talk about how this has changed in DLT. But first, let's talk about cost. So I originally had a dial that had like cost on one side, and it was a cost dial that had latency on one side and performance on the other, and then marketing took a look and they were like, no, that's terrible. You got to use a triangle. So I'm sure you've all seen the infamous Tradeoff Triangle. You have cost, latency, and performance as the 3 dimensions. You basically pick 2. So what are the controls that you have? First, you can control the cost of compute. And secondly, you can control the amount of work to do. What does that mean? So for compute costs, use cheaper instances. That's definitely one thing you can do. You don't always have to use the most expensive instance type. You don't have to use on demand. You kind of make these trade-off decisions based on what the SLAs are for your workload. A lot of customers use spot instances. A lot of customers, once you know what instance type you're going to be using for that job, it's probably not going to change. You get reserved instances and you're paying less. You're using things like auto-scaling and basically using only the compute capacity that you need at any given time. One thing that I want to sort of point out here is that a common pitfall for people doing this for the first time is that they don't realize that just simply reducing the amount of compute capacity without changing the amount of work that you have to do actually increases latency. It doesn't save you any money. It just makes things slower. What does that mean? Well, let's go back to my poorly drawn 12 squares representing Spark partitions. So let's say we have 12 units of work, and it takes 1 minute to process each partition. Now, let's say you have a 12-core VM. Okay, you have 12 CPUs. You can process this entire chunk of data in 1 minute because we're doing 12 things in parallel. And then you might be thinking, okay, well, you know what? A 12-core VM is too expensive. I'm going to use a 1-core VM for the sake of example, 1-core VM. So it's going to take me 12 minutes to run this. It's okay. My data can be 12 minutes late. No one cares. The problem is the way that costs are structured in most cloud providers. Running a 1-core VM for 12 minutes is the exact same cost as running a 12-core VM for 1 minute. So don't forget, you have to reduce the amount of work along with it. Okay? Now you might be thinking, this sounds complicated. I hope. I don't know. I'm judging by the faces I'm getting from the expressions. I see some snickering. All right. So that's where Lakeflow DLT comes in. Okay. So the first thing that I'd like to talk about, and I'm sure you've heard of this if you've been with Databricks for any period of time, the first thing that we've done to address I/O performance is introduce this concept of liquid clustering. Now let's talk about what the traditional problems were with Hive-style partitioning. It was very rigid, right? Like, partitioning is great. It's really good at like eliminating large chunks of data when you're filtering on in your query, but it's rigid, right? So in this example, let's say you have a customer table that's partitioned on 2 dimensions, customer and date, very simple, very common. But anyone that's worked with real-world customer data knows that volumes are different, right? Like, you'll have varying amounts of data depending on who your customer is. It could be a big customer, it could be a tiny one. And so what happens is that you end up with these partitions. Some of them are right-sized. Some of them have no data. Some of them have very little data, or the number of files are different. So it's not really great for I/O performance because you might be opening up way too many file handles for one partition and not enough for another. So how does liquid clustering solve this? Well, what if I told you that instead of having all of these files that are sort of like sparsely placed across these partitions, we can just go ahead and coalesce them across a dimension. Let's say for all of customer B or customer A, we can have one file that spans multiple dates, but not for every customer, right? And then same thing for the other dimension. Across a single date, we might be able to consolidate multiple tiny customers. It doesn't stop there. You can consolidate across multiple dimensions. So, tiny customers across several dates. That's kind of cool. But as Billy Mays would say, wait, there's more. You can also split this up. You can also split up larger partitions into smaller ones. That's kind of cool. Gives you a lot more flexibility. You don't have to really think about like limitations of partitioning. But you might be thinking, okay, Stephen, that sounds great and all, but you've already written all this data out, and that already existed. What about for new data, right? How does this look for things that I'm continuously ingesting on new days? So in the very beginning, you're going to be writing small files. But then as time goes on, as we start accumulating enough data to where it makes sense to start clustering these things, we can split these things out, again, on multiple dimensions. We have a table maintenance process that will come in and then consolidate all of these tiny files for you, so you end up with right-sized files. And then since we introduced liquid clustering, we also introduced clustering on write. So if you're writing lots and lots of large volumes of data, and it makes sense to cluster on write, we can absolutely do that as well. So we talked about the I/O thing. Who here has not heard of Photon? Raise your hand. All right. Well, I'm glad. So Photon is a vectorized query execution engine for Spark written in C++. It's much more efficient at doing math. It's much more efficient at doing joins. And it also is much more efficient at doing I/O operations. So when you're using Photon in Databricks, in DLT, or not, you're getting all of these performance benefits, specifically around CPU and around I/O. And then for those of you who have been to or have attended Summit in the past, you might have heard of something called Project Lightspeed, which is basically our effort to improve the performance of our streaming engine. And so we introduced the concept of microbatch pipelining. And again, looking back at history, for those of you that have CS backgrounds or have taken a CPU course at some point, you sort of know that Intel CPUs back in the day were much better than AMD CPUs because they were much better at pipelining. Right? They had way more pipes. You could do a lot more work and be more efficient about it. So let's take the microbatch example. In a typical streaming application, using microbatch processing, you go and figure out, okay, you're going to have a job that reads from a source, then you're going to do something interesting, and then you're going to write it out, right? Our 3 ETL steps. So here, stage 0, the very first square on the bottom left, that's our read job, okay? Well, that's our read app. That's our read. And then serially, after you read your data, you shuffle it across multiple stages, and then you write it somewhere. And then after that batch is done, you execute the next one. Everything happens serially, rinse and repeat. Now, what if I told you that in your stage 0, in your read, in your map operation, you needed 200 CPU cores to do that read. But then as you shuffle and reduce this data, you only need like 50. That means you end up with 150 idle CPUs that are sitting there doing nothing until your job is finished. Okay, and then the next batch begins, rinse and repeat. In microbatch pipelining, what we've done is we basically said, hey, look, we have idle CPU. We should be using it. And because every microbatch has known boundaries, this is part of the structured streaming's resiliency model, we can say, like, okay, we're done. We have 150 CPUs of capacity, or task slots of capacity. We can just go ahead and schedule the next microbatch to run. So this results basically in your end-to-end latencies going way down to 30% in our benchmarking. Better resource utilization. And then, who's heard of Enzyme? Who hasn't heard of Enzyme? All right. So, who's heard of materialized views? Any data warehousing people? Okay, cool. So, Enzyme is really, really cool as somebody with a data warehousing background. Because let's think about this. What is a materialized view? It's the output of a query, right? It's the persisted, stored output of a query. And you typically did this for what? Reporting, for things that were generally expensive to run, so we ran it once, and then everybody just looked at my output for some period of time. And then every day, every week, or however often it made sense, we'd just go and refresh that data. But for some time, you'd be staring at stale data. Enzyme allows you to go and incrementally update the output of your query when your source data changes. So again, we're reducing the amount of work that you have to do. You don't have to rerun these entire expensive queries and then rewrite all of that data. You're able to go and incrementally update it. And then it's kind of hard to have a conversation about autoscaling without sort of knowing the history of how autoscaling worked on Databricks. So I'll start with classical autoscaling. Way back when, for classic jobs and stuff. We had the concept of a cluster running in your data plane. We had the concept of a cluster manager in the control plane. And the cluster manager would periodically ping the cluster, see how busy it was, and ask basically, do you need more nodes to do your work? Okay. And then it would do this back and forth. It would add more nodes, and the cluster would scale out, scale down. But it was kind of like this back and forth was kind of slow. So it wasn't great for streaming applications where you needed to be a lot more reactive. And so in DLT Classic, we introduced the concept of enhanced autoscaling, where we basically moved the brains of the autoscaling operation onto the cluster. And so now you could be a lot more reactive about your scaling decisions. Well, now we have even more enhanced autoscaling, where instead of just adding more of the same node, we can actually scale vertically. So we can go from an XL to a 2XL, or 2XL to a 4XL, to address those pesky, like, out-of-memory problems, or those disk spill problems. And then finally, we have for TCO optimizations in serverless, you can actually pick two modes of execution. One is called performance mode, the other called standard mode. In performance mode, you basically get all the instant on hot standby nodes that you would expect from a serverless product. So you submit a job, nodes are already running, already have Spark running, executes fairly instantly. Comes at a cost, obviously. And we recently, in the past few weeks, have done a lot of sort of like refactoring on what that cost structure looks like. And so more of that to come in the upcoming keynotes and announcements. But from a performance perspective, performance mode is supposed to be about twice as fast as a classic cluster, classic non-serverless cluster running in your environment. Standard mode is supposed to have cost parity, TCO parity with what you have in your environment. Now the advantage here, again, like standard mode gets you all the great stuff that's in serverless. It also gets you zero infrastructure management. Now, one thing that I didn't touch on when we talked about cost was the whole like human capital aspect of things, right? Like engineering time, cost of, it's an opportunity cost, right? You can have your engineers focus on performance tuning. You can have your engineers focus on like, what's the best configuration to run my 500 jobs? Or you can let the system do it for you. That's why we're using a managed service, right? And we can focus our engineering time on other more important business critical things. So, putting it all together, we have Photon to address CPU concerns, to address some I/O concerns. We have liquid clustering that addresses the how do we reduce the amount of work that we have to do part. We have microbatch pipelining that helps sort of reduce that overall end-to-end latency and make your compute resource usage a lot more efficient. You have incremental MVs with Enzyme. Again, how do we do less work? We have enhanced autoscaling for better resource utilization. And then we have standard and performance modes to sort of help you balance that whole TCO decision. So, I'd like to end with a quote by another fictional character that happened to have the same name as the first guy. I'm going fast. All right.